We have a box of mass M attached to the ceiling as shown in the picture. There are 3 ropes. There's a tension force in each rope, and our task is to find the tension in each rope. So that will be the magnitude of the tension force in each rope A, B, and C. We see that the rope A is making an angle alpha with the ceiling, and rope B is making an angle beta with the ceiling. Rope C, on the other hand, is vertical. In this problem, the box is stationary. In other words, it's in equilibrium. It's in static equilibrium. It's not moving. It's not accelerating. So we will apply Newton's first law to this problem. We will actually do that twice. First, we'll apply Newton's first law on the box. And then we'll apply Newton's first law on this point right here, the intersection point of the 3 ropes. I'm going to call it point P. In most problems, usually we apply Newton's laws on an object, but we can also apply Newton's first law on a specific point. And this problem is an illustration of that. Let's start with the box. The first thing we need to do before applying Newton's first law is to draw a free body diagram for the box. A free body diagram is a diagram where we show all the forces acting on the object in question. First, we draw a coordinate frame. Usually it's a 2-dimensional coordinate frame, like the one I have here, an XY coordinate frame. And then with red arrows, I show the forces acting on the box. Now, what are those forces? The box has gravitational force acting on it. It has mass m, so it's being pulled by the earth towards the center of the earth, so the gravitational force is pointing down. And to represent the gravitational force, we are going to use F sub g. On the other hand, the box is attached to rope C, so it's being pulled by rope C upward. That's a tension force, so that's the arrow pointing up, the red arrow pointing up. In the free body diagram, I'm going to use F sub t for tension force. Because there are several tension forces in this problem, I'm going to label each one and name each one after the rope it is associated with. So this will be tension force from rope C, so that will be F sub t, and I'm going to use a superscript for that, so it's going to be F sub t superscript C, like so. F sub t, and this is the tension in rope C. And these are all the forces acting on the box. Now that we have all the forces shown in our free body diagram, we can go ahead and apply Newton's first law. Note that in this case, all the forces are in vertical. We have nothing going on in the x direction. All the forces are in the y direction, so we will have only one equation. Upward is our positive direction, so the tension force will be positive in our equation, and the gravitational force F sub g will have a negative sign in our equation. And let's remember what Newton's first law was. Newton's first law says that if an object is in equilibrium, net force acting on it is equal to 0. So in this case, the sum of the forces in the y direction will be equal to 0. Remember, we apply Newton's laws separately for each direction. So for y direction, we apply Newton's first law, and then if we had forces in the x direction, we would have to apply it separately along the x direction as well. But in this case, we don't have that. We only apply it along the y direction. Here's my statement of Newton's first law in the y direction. Sum of the forces in the y direction equals 0. In other words, net force in the y direction equals 0. This Greek letter capital sigma means sum, so sum of the forces in the y direction equals 0. So this is Newton's first law. This is the general statement, our starting point. In the next line, we will expand the left-hand side of our equation based on our free body diagram. So we will write down all the forces in the y direction with positive or negative signs depending on in which direction they're pointing, and set that equal to 0. Here I have the next line, plus Ft, that's the tension force pointing up because it's pointing up, and because that's our positive direction for vertical, that's positive, minus Fg, Fg is pointing down, and that's all, we don't have any other forces, equals 0. In the next line, I'm going to substitute m times g for Fg because by definition, the gravitational force acting on an object is equal to the object's mass times the gravitational acceleration, lowercase g. So that's the magnitude of Fg. And note that in an equation like this, all these variables are placeholders for magnitude. So when I say FTC, that's the magnitude of the tension force. I account for the directions explicitly with these positive and negative signs. So Ft and Fg are inherently positive because they refer to the magnitudes. Here I have substituted m times g for F sub g. Next, let's rearrange our equation to isolate the tension force in rope C. So that will be one of the unknown forces in this problem. If you add mg to both sides, we get Ft equals mg. So F sub t in rope C, the tension force in rope C, has magnitude equal to mg. Like so. Now let's go ahead and apply Newton's first law to point P. Here's the free body diagram for point P. There are 3 forces at point P, 3 tension forces, 1 from each rope. So the tension forces follow the directions of each rope. I have also included the angles from the picture. The tension force in rope A is making an angle alpha with the horizontal, and tension force in rope B is making an angle beta with the horizontal. This one is a 2-dimensional free body diagram, so we have forces in both x and y directions. That means we need to apply Newton's first law in the x direction and in the y direction separately. Let's start with the x direction. Here's our starting line. Net force in the x direction equals 0. In the next line, we will expand the left-hand side. Namely, we are going to explicitly write down the net force in the x direction. Now, if you look at the free body diagram, there is no force that is purely in the x direction. So there isn't any force that is horizontal. The tension force from rope C, which we already found actually, is purely in vertical direction. So that force is not going to go into this equation. On the other hand, the other 2 tension forces from ropes A and B have both x and y components. They're making an angle with x and y axes. So we need to figure out the x components of these forces for this equation. And keep in mind that the right word is the positive x direction and the left word is the negative x direction. So let's start with tension force in rope B. This is the vector representing that tension force, and we're looking for the x component of that tension force. If you focus on this triangle here, here's a 90-degree angle. Here's the angle beta, and the x component of this force is represented by this dashed white line, right? Because that's the x component is how much the force vector extends in the horizontal direction or in the along the x direction. And this distance here, this segment here, actually is the x component of the tension force. Now, because this segment is adjacent to angle beta, that would be a cosine. So the x component of the tension force from rope B is equal to the magnitude of tension force FTB times cosine beta. Is it positive or negative? Well, this force is pointing towards the upper right corner, and right is our positive x direction, so this will be positive. On the other hand, let's look at the tension force from rope A, and let's focus on this triangle here. Note that here's our 90-degree angle. So again, the force itself, the vector itself, is representing the hypotenuse of this right triangle, and that was also the case for the other force. Here's my hypotenuse FTA, and I'm looking for this horizontal segment again, the white dashed line that represents the x component of this force. And again, this segment is adjacent to my angle alpha, so that'll be a cosine alpha. So the x component of the tension force from rope A is equal to the magnitude of that force, FTA, times cosine alpha. Is this one positive or negative? The force is pointing towards the upper left corner, and left is negative, so this component will have a negative sign in our equation. Now we can go ahead and write down the equation representing Newton's first law along the x-axis. The first term, FTB cosine beta, that's the x component of tension force in rope B, and that's positive, pointing right. The second term, FTA cosine alpha, that's the x component of the tension force in rope A, with a negative sign since that force is pointing left. And these two add up to 0 by Newton's first law. Now in this equation we see that we have two unknowns, FTB and FTA, and this is only one equation, so we need another equation. Since we have two unknowns, we need two equations to solve for each unknown. What do we do next? Next we need to apply Newton's first law along the y direction. Basically we'll do the same thing along the y direction. Let's start with FTA. FTA is making an angle with the y-axis and the x-axis, so we need to find its y component. Now following the green dashed line and the angle alpha here, if we focus on this triangle, we see that the vertical dashed segment represents the y component of FTA. That's how much this force vector extends in the vertical direction. And with respect to the angle alpha, this green dashed segment is the opposite side, based on this triangle here, the right triangle, with this angle being the 90-degree angle. So the y component will go with sine alpha. In other words, the y component of this force is equal to FTA, the magnitude of the force, times sine alpha. And because the force vector is pointing towards the upper left corner, up is our positive direction for the y-axis, that is a positive component. On the other hand, for tension force in rope B, we can focus on this triangle right here. Here's my 90-degree angle. The force vector is the hypotenuse, and the angle beta is right here. So again, the y component, the vertical component of this vector, is represented by this green dashed segment, which is opposite of the angle beta. Again, that's sine beta then. So the y component of FTB is equal to FTB, the magnitude of the force vector, times sine beta, again with a positive sign because this vector is also pointing up. So that is our positive direction. Now, is that it? We have one more force, right, that has a y component, and that's FTC. FTC is along the y direction. It's in the negative y direction, but it's on the y-axis, right? So we don't need to calculate its component. It's purely in the y direction. We need to keep in mind that it's pointing in the negative y direction. So in our equations, it will have a negative sign. So that will be negative FTC. Let's combine all this and set up Newton's first law for the y direction. Here's what we get when we combine all that information. FTB sine beta, that's the y component of the tension force in rope B, plus FTA sine alpha, y component of the tension force in rope A, minus FTC, the tension force in the rope C, that is purely in the vertical direction, pointing down. That's why it has a negative sign. All that adds up to 0. So net force in the y direction is also equal to 0. So we have our final equation here. Again, we have two unknowns, FTB and FTA. Why am I saying that? Because remember, we already found FTC. We know that FTC is equal to mg. I have it right here. So in the next line, I'm going to go ahead and substitute mg for FTC, rewrite this equation, and then we will combine the two equations. We will solve the two equations together to find each of the other two unknowns. Here I have substituted mg for the tension force in rope C. It comes from the previous calculation. Now we have two equations, two unknowns, tension force in rope B and tension force in rope A. So what is the next step? The next step is to isolate one of the unknowns from one of the equations. There's more than one way to do it. Usually it's best to find the relatively simpler looking equation and isolate one of the unknowns from that. So I'm going to actually go back to this previous equation because it has less terms. It has like 2 terms as opposed to the other one that has 3 terms. I'm going to go back to this equation and isolate FTB from this equation. So I'm going to put everything to one side and FTB to the other side of the equal sign. So basically I'm going to add this term to both sides and then divide by cosine beta both sides to isolate FTB. Let's go ahead and do that. We have isolated FTB from the first equation. We are going to substitute this result in the second equation like so. Right here, wherever we have FTB, we are going to put FTA cosine alpha divided by cosine beta. So I'm going to go ahead and rewrite this second equation with FTB replaced with this expression. And that way I will obtain an equation that has only one unknown, and that will be FTA. So we can solve that equation. Single equation, single unknown, we can solve it. At this point, we're basically done with physics, and the rest of the problem is really mostly algebra. So I did a few steps here. The first thing I did was to replace FTB with this expression FTA cosine alpha divided by cosine beta. And here's the result of that. Here I have rewritten the second equation with FTB replaced with the expression involving FTA. So we have a single equation and a single unknown FTA. But we see that FTA appears in 2 separate terms, right? We'd like to isolate FTA, and it's appearing in 2 terms, so we need to factor it out from those 2 terms. In the next line, I factored out FTA. So I have one FTA here, another one here. I factor those out, and in parentheses I have 2 terms remaining. This comes from the first term and this comes from the second term. Also, another thing I did in this step was to add mg to both sides, so this expression is equal to mg. So basically the next step will be to divide both sides by this whole expression inside the parentheses. But we can rearrange it a little more. We can tidy it up a little bit. So in the next line, I multiplied and divided the second term by cosine beta so that we have a common denominator of cosine beta. So this is basically one single fraction. And in the next step, I'm going to divide both sides by this fraction, or multiply both sides by the reciprocal of this fraction, and that will isolate FTA. Here's the result of the final step of our algebra. We have isolated FTA and we were able to express it in terms of the given variables. So let's quickly verify that. M is the mass of the hanging box, that's given. G is a physical constant, it's always given. And beta and alpha are the given angles in this problem. So everything on the right hand side is given. That means this is basically the final expression for the tension force in rope A. And the last step will be to calculate the tension force or come up with an expression for the tension force in rope B. How do we do that? We go back to our equations, and remember here we had already isolated FTB and expressed it in terms of FTA. Now that we know FTA, we'll just reuse this equation and replace what we found for FTA right here, and that will give us an expression for FTB again in terms of the given variables, namely M, alpha, and beta. Here I have replaced FTA here with the expression that I found here, mg times the big term in parentheses with angles, cosines, and sines. And then we have a term of a factor of cosine alpha divided by cosine beta at the end. So I put those here as well. So this is what we get for FTB, the tension force, the magnitude of the tension force in rope B. This is a big expression. It could be simplified a little bit. I have cosine beta here in the numerator and cosine beta in the denominator. These cancel. So we can rewrite it in a slightly simpler way. This is what we get after the factor of cosine beta cancels out. We get mg times cosine alpha divided by cosine alpha sine beta plus cosine beta sine alpha. So that is the magnitude of the tension force in rope B. Again, we were able to express it in terms of the given variables. M is the mass of the box, G is a physical constant, and alpha and beta are the given angles in this problem. Note that the expressions for FTA and FTB are fairly similar. Both are mg times, this factor or this expression involving angles. Also note that the dimensions are consistent. M times g, that's mass times acceleration, that is equivalent to force in terms of physical dimensions. And the expression in parentheses is dimensionless. Cosines and sines have no physical dimensions, so the right hand side of each expression has the dimensions of force.